Alright, today we're going to start talking about the relativity of time. We've already begun talking about this, but now I want to talk a little bit about the math involved in it. Alright, so I told you guys this was not going to be a math-intensive chapter. The math is more to explain exactly how this works rather than, a set assignment. There will be a couple of practice math problems for you to do, but still, I'm just saying that this is more of a way of proving the concept than it is of pounding out math problems. Alright, now, the first thing that we got to realize here is time is relative. Now, the relativity of time comes from the fact that the speed of light is constant no matter the reference frame. Okay, now I used the explanation of this one as if you were driving in a car on I-79 and you were doing, let's say you're going the speed limit here at 65 miles per hour, and someone else is coming past you at 95 miles per hour. Now, depending on what's going on here, if you're a person in this car right here, you are going to observe the other vehicle traveling next to you at 30 miles per hour relative to your vehicle. Sorry, check that. This person will observe the other vehicle Sorry, my drawing is not on point today. Alright, so the observer in this vehicle is going to see this other car passing at 30 miles per hour. An observer in this car is going to observe this vehicle traveling backwards at 30 miles per hour. Alright, so in each individual reference frame, you would be able to see there's a slight difference here, where this one is observing this one traveling faster or forward at 30, this one is seeing this one traveling backwards at 30, and if someone was an observer from outside watching this entire setup here, you'd be seeing both vehicles, one traveling 65 miles per hour, one traveling 95 miles per hour. All of this would be able to be tested. Okay? Now, the interesting stuff happens when you get into a rocket ship out in space. Okay? Alright, so here's you in your rocket ship, and there is a particle of light, a photon, traveling this way right here. That photon is traveling at the speed of light. So if you are watching that photon, let's say that you're traveling at 0.95 c. You're going 95% the speed of light. If you look at that photon right there, you will see that photon traveling forward at c, not at 0.05 of c. The speed of light is still going to be constant. The speed of light is not going to change. It is always going to be the same exact value. Now, if there was an outside observer here as well, observing that light would be traveling forward at the rate of c. Alright, so this is what they mean by the fact that, well, the speed of light is absolute. Alright, no matter what, if an object is traveling the speed of light, it will be traveling the speed of light in every single reference frame that there is. Alright, now, this is a definition that is stated on page 1029 in your textbook. I'm going to write it out. I'm actually going to type it out because it'll be faster. Alright, now, In the yellow box on the top of page 1029, it says when two events occur at the same time. Or I'm sorry, at the same location in an inertial reference frame. An inertial reference frame is just a reference frame in which physics works. The time interval between the two events, or them as the book calls it, measured in that frame, is called the proper time interval, or proper time. Measurements of the same time interval from any other inertial reference frame will always be greater. Now, what that means is we've got two events happening at the same place, same time. Alright, so let's say that you have a flash of light here, and then a few seconds later that flash of light bounces off of a mirror and comes back down. Alright, those two events are occurring at the same location in some inertial reference frame. That means that in this frame itself, in the frame at which it happened, that is going to be the shortest time interval that can exist. So basically what you're looking for is, you're looking for the place where the action is. Alright, where the action is, we'll have the smallest time. Alright, I used this as an example last year. If you were to hop on a Concorde jet from London to New York City, and your mother were to hop onto a regular jet from London to New York City, both of you with the same exact watch setting, both with the same exact timing on the watches, when you got to New York City, the two watches are going to be slightly off. The one where the action is, the one with the faster reference frame, is going to have a slower time on the watch. Less time will have elapsed in that time period. Okay, now let's look mathematically at what happens here. The basic equation that it has is the change in time is going to equal okay, this is the generic equation right here. Now this is assuming you know exactly what the original time was, and you're trying to stretch it to a different inertial reference point. Okay? Now, notice what's going on in this equation right here. This is time for an observer outside. In other words, a person who is not moving or not involved in the action. Alright? This would be the time observed at point of interest. Alright? Now, the bottom part here is normally used as called the Lorentz equation. We'll talk about that in a couple of minutes here. But down at the bottom, we've got, first of all, the square root of 1 minus v over c squared. Now I want to take a look at this part right here first. Notice that v over c, first of all, we cannot travel faster than c. Alright, so this is always going to be bigger, and this is always going to be smaller. Alright, so what that means here is as this one gets larger and larger and closer to c, it will never, ever, 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 ever reach 0. Or I'm sorry, reach 1. Okay? V cannot reach c. Now that is important, because think about it. If we had v being the speed of light, or c divided by c is 1, 1 squared is 1, 1 minus 1 is 0, what that will do is that will turn our time interval from some value into some number divided by 0, which is going to give us an infinite value. So the speed of light can never be actually reached in this equation. All right? The speed can never reach c. Now what that means is we're always going to have some fraction, some value that's less than 1. You take some value that's less than 1 and square it, you're going to get a number that's even more less than 1. 1 minus that number is going to give you a relatively small number, depending on this guy right here. Now what I want to do here is, let's say that we've got a generic instance where you're traveling, let's say Mach 1. Alright, the speed of sound. So, and let's say that the observed time interval was 0.1 of a second. So, we've got 0.1 divided by 1 minus v over c squared. Alright, now, if I'm going the speed of sound, and let's just make it an easy number here, we'll call it 340. So, delta t equals 0.1 divided by, well, square root of 1 minus 340 over 3 times 10 to the 8th meters per second squared. Now, meters per second. Nice thing is, meters per second divided by meters per second, units are going to cancel out. I'm going to have a time of seconds up top here. The end unit is going to be seconds. So, 1 minus 340 over 3 times 10 to the 8th. Let me get my emulator up here. Where'd it go? Bobby, Testiani. Oh, hey, I'll just use theirs. Alright, so my calculator, math tools, calculator. Alrighty, so 340 divided by 300 million equals 0.000001. Okay, now I need to take that value and square it. Well, here's the problem. When I square that, that makes it 0.00000, 1, 2, 3, 4, 5, 10 zeros, and then a 1, which this calculator is assuming to be 0. So, if I take 0.1 divided by 0.1, 2, 3, 4, 5, 6, 9, 10, 1. The calculator treats that as 0. So what that means is, if the time interval is this small here, there's going to be no overall change in time based upon you just simply going Mach 1. So let's change it to Mach 10, or 10 times the speed of sound. Let's see what happens. The change in time equals 0.1 divided by the square root of 1 minus 3,400 over 3 times 10 to the 8th. Alright, now what I'm trying to get you guys to see here is the smaller your speed is, the less impact overall this is going to have on the time dilation, the stretching of time. So 3,400 divided by 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 17. Oh, whoops. I got one too many. 1, 2, 3. All right. Million. Okay. Equals. All right. Got a little bit bigger of a number. Now when I square that, unfortunately, once again, I'm still at 0. Now that means that 1 minus 0 is going to be 1. 0.1 divided by 1 is going to give you 0.1. So even at 10 times the speed of sound, or 3,400 meters per second, you still have no change in your delta t. You need to get yourself up to approximately, let's say, a third to a half of the speed of light before you can really start getting any stretches here. But let's put it to a neat situation here and see what goes from there. Let's say that now you're able to travel at 0.95 times the speed of light. 95% of the speed of light, which would be 285 million meters per second. All right? Now, this is where things start getting interesting. That change in time equals, and let's say that we're going to make it for a longer period of time. Let's say the original event took 10 seconds divided by square root of 1 minus 0.95 c over c squared. All right? Now, one thing that a lot of your college professors are going to ask you to do is leave things in terms of variables as long as you can. Here's why. I've got 0.95 c up here, and I've got c down here. C will cancel with c. So all I really have to do is take 0.95 and square it. Okay? So this entire chunk over here turns into 0.9025. So I take 1 minus, pardon me, 0.9025 equals, and now I'm going to finally get some changes here. All right? When I take that, I take 10 divided by that. That 10-second event that happened in real time in the inertial reference frame now has increased by 102.56 seconds to someone to the outside. So that means that if you were outside looking in on this, you would have seen a 112-second, almost a 2-minute event happening in what the actual event was only 10 seconds. Now, this is where the stretches in time actually happen. It always will be greater for an observer from the outside. So if you're watching that spaceship travel, that spaceship is traveling for 102.56 plus 10, or 112.56 seconds. But the actual event of the people on that spaceship would have only been a 10-second duration. So basically, what's happening is time is going slower here than it is up here. Now, let's look at a couple of the generic equations that they have here. Now, first of all, they call the Greek letter beta here to be they call beta to be v divided by c. That's just a simplification to make the equation look a little bit prettier as they're working. It doesn't really serve any real purpose other than to kind of just give you a general representation of what the overall speed is compared to the speed of light. All right. Now, the other thing that they will do here is what's called the Lorentz factor. With the Lorentz factor, all right, they use the Greek symbol gamma. gamma equals 1 over square root of 1 minus beta squared, where beta is simply V over C, and everything else is pretty much as it is. Okay? Now, by using the Lorentz factor, and the reason they use this is it's useful in more than just time. We're going to use this in length dilation as well. But anyway, the Lorentz factor just kind of simplifies this up to make it a little bit prettier. So what this means is the overall change in time equals gamma times what the overall change in time for a different reference frame equals gamma, or the Lorentz factor, times the original time observed. Even though this zero is normally called naught, what I like to call it is observed when we're talking about this relativity stuff, because it makes it a little bit easier to understand what's going on. Now, if you were to take this and just look at what it means, that means delta t equals gamma, which is 1 over square root of 1 minus beta squared times delta t naught, or if you actually expand this out, delta t equals delta t naught over square root of 1 minus V over C squared. Okay? Now, a couple of things I want you to notice out of this, and the biggest points that I want you to take out of it, all right, is number one, the faster you're going, the greater the stretch of time. Now, I don't want you to sit here and think that if you're driving 125 miles an hour down the road, that this is going to make your life longer, or it's going to make your day longer, or it's going to change anything about that. 95 miles per hour is a drop in the hat. 120 miles an hour is a drop in the hat. It turns out that the speed of sound is 750 miles per hour. 750 miles per hour did 0 to change overall time. 10 times the speed of sound did almost nothing. Now, so what that means is, as you go closer and closer to the end value of C, the faster you're going, the greater the stretch of time is going to be. The second thing, man, I'm having a complete brain fart. All right, the faster you're going, the greater the stretch of time. The second thing, I'm going to pause this for a second and try to remember what my answer was supposed to be. The second thing, you cannot travel at or above the speed of light. You cannot travel at or above the speed of light. If you do travel at or above the speed of light, there's two things that happen. Number one, you will actually get the delta t in your time interval to become 0 if you're able to travel at the speed of light. If you're able to travel above the speed of light, what that will actually do is allow you to travel backwards in time. Now, due to the thermodynamic arrow of time, we know that to be impossible. So we got to say that this cannot happen. All right? And the third thing, the time observed will always be shortest in the original reference frame. Okay? Now, if anyone is struggling with any of these topics, I suggest that you read pages 1027 to 1029 in your textbook. They have a couple of additional examples on 1030 as well, and there's a practice problem on 1031. Now, there will be a homework assignment. I probably will not give that to you actually until tomorrow, but we'll see where we end up. If you have any questions or problems about this video, email me, let me know, and we will get back to you as quick as I can. Good luck and enjoy.